Hi, it's Steven here again, and I'm going to be talking about an introduction to calculus for statistics and probability. So just an overview of what I'm going to talk about in this video. I'm going to review some distributions. Then I'm going to be talking about limits. Then I'm going to be talking about derivatives, and I'm going to finish with integrals. As usual, the textbook that we are using is A Modern Introduction to Probability and Statistics. This video is going to be pretty long, so you might not be able to watch it all in one sitting. If you need to pause and come back, or just fast forward to sections that you feel like you need to review first, then feel free to do that. I would recommend that you stick around for the entire presentation, just because I think, throughout the presentation, I'm going to be giving you helpful, tips and things that you should keep in mind when you're working with particular distributions, limits, derivatives, and integrals. So before getting into the material, I want to talk about why is calculus important. So distributions help us model probability, and calculus helps us compute it. Calculus helps us to understand relationships between variables. For example, isolating the variable we want to measure. Calculus can help us do that. Calculus helps us to investigate variables as well. For example, what is the expected value of x? What is the variance of x? If x is a continuous variable, then we can use integration to help us determine these values. Furthermore, calculus is essential for success in this course and for future statistics courses. So just working with calculus in general, or being able to work with calculus in general, is very important. Okay, so we'll start with the probability mass function. This can be found on page 43 of the textbook. So by definition, the probability mass function p of a discrete random variable x is the function p such that it maps the real numbers to the bounded region 0, 1, and is defined by p of a is equal to the probability that x equals a for a between negative infinity and infinity. This is used for all of our discrete probability distributions, such as the Bernoulli, binomial, negative binomial, geometric, Poisson, and hypergeometric distributions. One of the things I wanted to mention about the probability mass function is that essentially it's mapping every value to a probability. So for example, you're wondering what the probability that if x is rolling a die, then we're looking at the probability that x can take on a certain value, so that x is 1, for example, and that would be 1 over 6. So it's mapping each outcome of a random variable to the probability of that outcome. Alright, so moving on to the probability density function, or the PDF. This is on page 56 of the textbook. So by definition, a random variable x is continuous if for some function f, which maps real numbers to real numbers, and for any number a and b such that a is less than or equal to b, so we're looking at a bounded region here, the probability that x is between a and b is equal to this integral sign, a to b, of f of x dx. So we're going to talk about this more later, but essentially what this is telling us is that the probability that x is between a and b is equal to the area under the curve f of x from a to b. So we'll talk about that more later. But anyways, the function f has to satisfy f of x greater than or equal to 0 for all x, and the integral from negative infinity to infinity f of x dx is equal to 1. So these are both important aspects, important facts. So before we were talking about the probability mass function, and now we're talking about the probability density function. The probability mass function can be seen as a way of mapping the particular outcomes to probabilities. However, the probability density function is not quite the same thing, because since we are working with a continuous variable, each outcome of a continuous variable cannot have its own probability. And the reason it can't is that if you were to add up all those probabilities, you would get a number greater than 1. You get an infinity, actually, because there's infinitely many points. So the probability density function is more so seen as a tool used to figure out the probability of a variable being in a certain region. And we'll get more into that later, but the probability density function does exhibit a lot of the same properties as the probability mass function. So for example, f of x is greater than 0 for all x. So although f of x does not represent a probability, it is a positive value, or equal to 0. And if you were to sum over the entire range of possible values of x, we would get, if we took that area, we would get 1, which is, again, very similar to if you were to add up all the possible outcomes, the probability of all the possible outcomes, you would also get 1 for the probability mass function. So the probability density function is almost the same as the probability mass function, but except for continuous variables instead of discrete variables, but there are some subtle differences. So we call f the probability density function, or probability density of x. And of course, since this is used for continuous random variables, we use this for distributions such as the normal distribution, the uniform, the exponential, the gamma, and the beta distribution. Alright, so moving on to the distribution function. So this is also known as the cumulative distribution function, or CDF. And this is used for both continuous and discrete random variables. So they're actually, it's a similar definition, or it's the same definition for both continuous and discrete random variables. So by definition, the distribution function f of a random variable x is the function f such that it maps all real values to the region, the closed region 0, 1, and is defined by f of a is equal to the probability of x less than or equal to a for a between negative infinity and infinity. So I'm going to stress this right now, but it's also something that I'm going to stress throughout the entire review session, and that is that understanding the technical definition of a function, or of understanding the technical definitions of terminology, is good, but it's not the most important. The most important thing that I want you guys to take away is understanding the meaning, or understanding knowing the definition is not super important, but understanding the definition is what's important. So knowing that, okay, a distribution function f is a random variable x such that it maps to real numbers to 0, 1 is defined by f of a is equal to probability of x less than or equal to a for a is between negative infinity and infinity. That's important, but understanding what that represents. And when you're trying to understand what it represents, this is where the cumulative distribution function name comes in handy. So if someone were to ask you, what is a distribution function? What does it mean? Then you could provide this definition, but what it's really saying is that instead of looking at the probability that x takes on a certain value, we're looking at the probability at a cumulative probability that x takes on a value less than or equal to a given value. So that's key with the distribution function. It's actually the reason why when I first learned it, it was called the cumulative distribution function, and that's something that's always how I'm going to see it when I think of distribution function. It's the cumulative distribution function, because we're looking at the cumulative probability. And then yeah, so it's also important to know, but more importantly, understand the definition of a probability density function and a probability mass function. So for a probability mass function, this is seen as like the mapping from all of the outcomes to the probability of each of those outcomes. Pretty straightforward. It's basically like a probability function that we've seen in previous chapters. So there's nothing new here. But the fact that A can be any value tells us that for a lot of these probabilities, it's just equal to 0. All right, so the probability density function. What a key takeaway is from here is that the probability density function doesn't give us, or the output of plugging in a specific x value into the probability density function does not give us a probability. Rather, the probability density function is a tool to calculate a probability. And we use it as a tool because we need to actually integrate over the probability density function. And that's how we get our probability. And when it comes to continuous random variables, you can't actually get a probability for a particular value. You can only get a probability for a range of values. So that is basically the key takeaway from the probability density function. All right, so in terms of distributions, I'm not going to spend too much time on each distribution, but I'm just going to quickly go over their definitions and where you can find them. So the Bernoulli distribution is on page 45, and by definition, a discrete random variable x has a Bernoulli distribution with parameter p, where 0 is less than or equal to p, or is less than or equal to 1, if its probability mass function is given by p sub x of 1 is equal to probability of x equals 1, which is equal to p. And p sub x of 0 is equal to the probability that x equals 0, which is equal to 1 minus p. We denote this distribution by Ber of p, and we use this as a way of measuring an event with only two outcomes, success and failure. We assign the parameter p to the probability of success. So when you're trying to construct whether or not a given scenario is a Bernoulli, trying to determine whether or not it's Bernoulli or not, you need to determine, is it an event that only has two possible outcomes, success or failure? And then you need to determine what probability you want to assign to the probability of success, and then the probability of failure is going to be 1 minus p. Next, the binomial distribution. So by definition, a discrete random variable x has a binomial distribution with parameters n and p, where n is any integer from 1 to infinity, and p is between 0 and 1. If its probability mass function is given by p sub x of k is equal to the probability that x equals k, which is equal to n choose k, times p to the power of k times 1 minus p to the power of n minus k, for k is equal to 0 to n. We denote this distribution by binomial of np, and this is used to count the number of successes or failures of n Bernoulli trials. So I'm not going to talk too much about the binomial distribution, but it's very similar to the Bernoulli distribution, except you're just repeating the trial n times and seeing how many successes you get over n trials. The understanding this formula is not too complicated. So we have k successes, or we're trying to determine the probability of k successes. So we have n total trials, and we're choosing k of them to be successes. So that's this n choose k. And then since we have k successes, we have p to the power of k, and we have n minus k failures, because that's the complement of k. And then the probability of that is 1 minus p. All right, so the geometric distribution. By definition, a discrete random variable x has a geometric distribution with parameter p, where p is between 0 and 1, if its probability mass function is given by p sub x of k is equal to the probability that x equals k, which is equal to 1 minus p to the power of k minus 1 times p, for k is equal to 1 all the way up to infinity. We denote this distribution by geo of p, and this is useful when we're measuring the number of trials until the first success. Alright, now the negative binomial distribution. A random variable x has a negative binomial distribution with parameter r and p. R is the number of successes we are looking for, and p is the probability of success in each trial. If it has the probability mass function, because we're working with a discrete random variable, p sub x of k is equal to k minus 1, choose r minus 1, times 1 minus p to the power of k minus r, times p to the power of r, where k is equal to r all the way up to infinity. So k is the number of total trials that we're doing, and r is the number of successes. So we're trying to determine the probability that it will take k trials to get r successes. And so we know that the last trial has to be a success. So we only have k minus 1 trials that we're not sure where the successes are. And so there's k minus 1, choose r minus 1 ways to arrange those successes and failures. And then we have k minus r successes, k minus r failures and r successes. And that's where those terms come from. In notation, we write x is distributed with a binomial distribution, negative binomial distribution with parameters r and p. And it's important to note that the geometric distribution is actually a special case of the negative binomial, and this is when r is equal to 1, when we're only waiting until the first success. Moving on to the Poisson distribution. By definition, a discrete random variable x has a Poisson distribution with parameter mu, where mu is greater than 0 if its probability mass function p is given by p of k is equal to p of x equals k, the probability of x equals k, which is equal to mu to the power of k divided by k factorial times e to the negative mu. And this can be for k is equal to 0, 1, 2, all the way up to infinity. So this is a discrete probability function. We denote this distribution by Poisson of mu. And in order to use a Poisson distribution, you need certain criteria to be satisfied. One of the criteria is the homogeneity property. And this means that the rate of which events occur, which is mu, the rate parameter, is constant over time. And you require the independence property, which means that intervals of occurrence are independent. And we also need, so the rate and the intervals are independent. I believe that covers the requirements for the Poisson distribution. All right, the uniform distribution. By definition, a continuous random variable has a uniform distribution on the interval alpha beta if its probability density function f is given by f of x equals 0 if x is not in alpha beta, and f of x equals 1 over beta minus alpha for x between alpha and beta. So what it's saying is that it follows a uniform distribution on a particular interval, and any other possible x value outside the interval is actually equal to 0. So we denote distribution by u of alpha beta, and uniform distributions are useful when x is equally likely to take any value over a given region. So sometimes you will get questions that don't explicitly give you the probability distribution, but they'll give you information such as x is equally likely to take any value over a given region, or any sort of information that indicates to you that x is uniform over a particular region. The probability of x taking any of the values is the same. And if it's continuous, that is also important for the uniform random variable. Next, the exponential random variable. or the exponential distribution. So a continuous random variable has an exponential distribution with parameter lambda if its probability density function f is given by f of x equals 0 if x is less than 0, and f of x equals lambda e to the negative lambda x for x is greater than or equal to 0. We denote this distribution by the exponential lambda, exp lambda. And this is useful when we're considering a rate that occurs continuously. So continuously decaying objects or properties, then you would want to use an exponential distribution. All right, the normal or Gaussian distribution. So they're both the same distribution, just a different way to say it. So by definition, a continuous random variable has a normal distribution with parameters mu and sigma squared greater than 0 if its probability density function f is given by f of x is equal to 1 over sigma times the square root of 2 pi times e to the negative 1/2 x minus mu over sigma all squared. And this is for any x from negative infinity to infinity, so any x in the real numbers. We denote this distribution by n of mu sigma squared. And sometimes you'll see a notation for the Gaussian distribution is slightly different as n of mu and sigma. So sometimes instead of using the standard or the variance, it'll be the standard deviation. The normal distribution is a very cool and important distribution to know. If there's any distribution that you remember from this course moving forward, hopefully you remember more than just one distribution, but if you only had to pick one and decide how you're going to fit all this knowledge in your brain, the normal distribution is the distribution to take away. So it's really cool, and I recommend Googling some of the properties that it has because it occurs in nature all the time, and it has some other special properties. So for example, it is symmetric around its mean, it frequently occurs in nature, and it has the bell curve shape. All right, moving on to the gamma distribution. So by definition, a continuous random variable x has a gamma distribution with parameters alpha greater than 0 and lambda greater than 0 if its probability density function f is given by f of x equals 0 for x is less than 0 and f of x equals lambda times x to the power of alpha minus 1 times e to the negative lambda x over gamma of alpha for x is greater than or equal to 0, where the quantity, I believe this is the rho symbol, capital rho of alpha. Or no, I think this might be the capital gamma letter. I'm not sure. Probably double check that. But this capital, I'm going to say gamma of alpha is a normalizing constant such that f integrates to 1. And we denote this function by gamma of alpha lambda. So review, I'm going to say this because the gamma function is kind of interesting. You don't need to understand exactly how the gamma function works, but there's a couple properties that you should know when trying to solve questions involving the gamma distribution. So please review the gamma function and its properties. I believe this is in the textbook around page 157. The gamma distribution is used for queuing models, climatology, and financial services. I think most of the examples in the textbook, well, I think the examples vary, but you're probably most familiar with the queuing models, which is like the amount of time for a series of exponential variables to complete. Moving on to the Pareto distribution. So by definition, a continuous random variable has a Pareto distribution with parameter alpha greater than 0 if its probability density function f is given by f of x is equal to 0 if x is less than 1, and f of x is equal to alpha divided by x to the power of alpha plus 1 for x is greater than or equal to 1. And we denote this distribution by Pareto par of alpha. This is often used to describe social, scientific, geophysical phenomena in society. Feel free to Google and learn more. A lot of these distributions are pretty cool and come up a lot in the real world. All right, so that finishes the review for distributions, and now I want to talk about limits. So hopefully you've heard of this term before, but if you haven't, I'm going to try my best to do a good run through of what you need to know about limits for this course. So consider the function f of x is equal to k times 1 minus e to the negative lambda x for x is greater than or equal to 0, or x greater than 0. So what values of k make this a distribution function? So think about that for a second. If you go back to the definition of a distribution function, it should tell you that the probability of so f of x is equal to the probability that x takes on a value less than or equal to x. So there's big X, which represents a random variable, and small x, which represents a particular value. So I believe they use f of a, right? So it's probability that the random variable x is less than or equal to a. So one of the things that hopefully either you have noticed already or you haven't noticed, but if you consider the probability that x is less than its maximum value, that has to equal 1. Because from the upper bound to the lower bound of all possible values of x, if you sum up the probability over all of that, it has to equal 1. And that's the definition of a probability function. So when we know that, so first of all, let's assume that it is a distribution function, and then we'll try to solve for k. So assume f of x is a distribution function. Then we know that the probability over all x has to equal 1, right? Because that's just part of the definition of a probability. So thus, for w arbitrary close to infinity, f of w, which is equal to the probability that x is less than or equal to w, equals 1. Right? Because the closer that x gets to infinity, the closer that w gets to infinity, we're now looking at the probability that x is between 0 and infinity. And because that covers the entire domain of values for x, it has to equal 1. So we know this has to equal 1 if in fact it is a distribution function. And that's what we're trying to figure out. So we know that this is going to be equal to k minus k times e to the negative lambda w, because we're given the distribution function right here. And this equals k because if we look at this term right here, we have this e to the power of negative lambda w. Well, if w is approaching infinity, lambda is just a constant. So we know that e to the negative lambda w is going to be arbitrarily close to 0. And since it's close enough to 0 for all intents and purposes, that just becomes 0 and k equals 1. So thus k equals 1 makes f of x a distribution function, and 1 minus e to the negative lambda x is actually the distribution function for x being a exponential random variable with rate lambda. Alright, so let's go on to a limits definition. So I want to preface this by saying understanding the definition, knowing the definition of a limit is not super important, but understanding what a limit is important. So let's just jump into the definition. So let f of x be a function defined on an interval that contains x equals a, except possibly at x equals a. Then we say that the limit as x approaches a of f of x is equal to L. So it's equal to a value. If for every number epsilon greater than 0, there is some delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is between 0 and delta. Sorry, I think I read that wrong. But so if every time, this is the limit if for every number epsilon greater than 0, there is a number delta greater than 0 such that absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta and greater than 0. So in general, substituting L for the limit of f of x as x approaches a will be sufficient, but sometimes you will need to consider what this limit is approaching. So here's some examples of some common limits as x approaches positive or negative infinity. All of these are important, so I would recommend memorizing these. Actually understanding them would be nice too, but as tools for solving questions, I recommend at least memorizing these. And you can find these at this website, this calculus cheat sheet limits. And so yeah, please review these if you do not know them already. All right, so now I want to talk about in the instance that you have a multivariate function. So if we're taking the limit of a multivariate function, which means there are more than one variable, we hold the other variables fixed. So consider g of xy, which is equal to x times y. Then the limit as x approaches 23 of g of xy is equal to y times the limit of x as x approaches 23. And the reason we can do this is because y is not affected by x, and we are only considering x as x approaches, the limit as x approaches 23, right? So because as x approaches 23, it's just 23, we can plug that value in and we get 23y. However, if x was approaching infinity, then we would have y times basically infinity, and that would just be infinity. All right, so that covers the limits for the most part, or what you need to know for this course. So moving on to derivatives, if you look at, we'll start with an example. So what is the rate of change of the function f of x equals x squared at point x equals a? So hopefully this kind of rings a bell in your head. You think rate of change, okay, that's probably derivative. Derivative is the instantaneous rate of change. So, okay, so let's just see how we would go about solving this using like a limit, for example. So we can actually solve this by using the equation of a slope. So equation of a slope is, so the slope is the rate of change. These are analogous, very like synonyms. So we know the equation of a slope from high school is delta, the change in y, divided by the change in x. So we have f of x minus f of a divided by x minus a. And since we are interested at the slope at a particular point, we can calculate this by taking the limit as x approaches a. Because we're only interested at the slope at x equals a, not from x to a, right? So we can do this by taking the limit. So we get limit as x approaches a of f of x minus f of a divided by x minus a is equal to the limit of x as x approaches a of x squared minus a squared divided by x minus a. So you might think, okay, Steven, like you said, we can just plug in the value for a limit. But in this case, it actually won't work, because if you plug in x equals a here, the denominator is 0 and this whole fraction becomes undefined. But cleverly, we can actually factor the numerator using difference of squares. Hopefully you remember that from high school. That becomes x minus a times x plus a. The x minus a's cancel out, and we get the limit as x approaches a of x plus 2a. And now we can plug in our limit value because we don't get an undefined number, and that's just 2a. And this should align with your intuitive definition of a derivative, where you just bring the 2 down, you decrement the exponent by 1, and you bring it down. And so f of a would just be 2, or f prime of a would be 2a, and that's what we got here. So this is kind of a little bit of an intuition behind the definition. So the definition of a derivative states that the derivative of f of x with respect to x is the function f prime of x, and is defined as f prime of x, which is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. This is another representation of what we did on the previous slide, except now we don't have x and a's, we just have x and h. And in this case, h is representing the difference between x and a. And so as h approaches 0, the difference between x plus h and x becomes 0. And so now we're looking at that instantaneous slope at that particular point. Again, knowing this definition is nice, but it's not it's not what you need to solve the questions. What's important is being able to understand what is a derivative. Like, what is the derivative telling you? Well, it's telling you the instantaneous rate of change at a particular point. It's giving you the slope of the tangent line at that particular point. And we can use that to help us solve questions. All right, so these are a list of common derivatives, and you should know all of them. If you don't know all of them, I highly recommend memorizing them. And there's a sheet of common derivatives and integrals if you want to learn more information. All right, so let's move on to another example. What is the derivative of x plus 1 cubed with respect to x? So usually we have some sort of function associated with it. So I introduced the let statement here, and I think that's a good idea to solve this question. So let a of x equal x plus 1 cubed. We want a prime of x. And we can also write this as dA over dx. And this symbolizes the derivative of a with respect to x. We have that a of x is equal to x plus 1 times x plus 1 times x plus 1. And if we expand that, we get x cubed plus 3x squared plus 3x plus 1. Therefore, a prime of x, the derivative, is equal to 3x squared plus 6x plus 3. All right, so another great tool, and I want to emphasize this. I think it's on the list of, yeah, so it is here. It's called the chain rule, but I wanted to dive into it specifically because it's a very important tool in this course and moving forward. So the chain rule is a formula that helps us take the derivative of a composite function. So consider the function h of x, which is equal to f of g of x, where f and g are both differentiable functions. We have that the derivative of h is h prime of x, which is equal to f prime of g of x times g prime of x. So we're basically taking the derivative of the outer function, f of g of x, it's just going to be f prime of g of x, and then we're going to take the inner function, g of x, we're going to take that, and we're going to take the derivative of that with respect to x. So what I like to think about when I'm solving these questions is, when I need to use the chain rule, I'm taking the derivative of the outer function times the derivative of the inner function. Now, it's not exactly what's going on, or it's basically what's going on, except for the fact that the outer function still has g of x in it. It's not just f of x. But it's a good way to remember what the chain rule is when you think of it like derivative of the outer times the derivative of the inner. And what happens if g of x itself is a composite function? Well, we can just repeat the process. So we can substitute g prime of x for p of x times, or p of q of x. So it would be p prime of q of x times q prime of x, for example. So it's cool because the chain rule can be repeated as many times as you need. Another representation, and this representation I'm going to say is a lot better. It's a lot more, it's a lot easier to read than all these brackets and whatnot. So this is the notation that I use now if I ever need to use the chain rule. And so I highly recommend learning this form of writing the chain rule. This form is also nice as well. It's just another way. If this form is easier to understand for you, then you can stick with this form. So here we have the derivative of h with respect to x, which is equal to the derivative of h with respect to f, times the derivative of f with respect to g, times the derivative of g with respect to g with respect to x. And this is just another form of writing this equation. And what's cool here is that we can see clearly how we got from derivative of h with respect to derivative of x to derivative of h with respect to derivative of x. Because although these aren't physical numbers, these operators can work like multiplicative factors. And if we cancel out this df, this df and this df, and this dg and this dg, we just get dh divided by dg. And so dh over df is equal to 1 because the coefficient of f is 1. And once this becomes 1, this is equal to this right-hand side is equal to this right-hand side. And so it really becomes clear at that point. All right, so now that we know about this chain rule, let's tackle example 2 again, but using the chain rule. So what is the derivative of x plus 1 cubed with respect to x? We can use the chain rule. So if we let h of x equal x plus 1 cubed, we let f of x equal x cubed, and g of x equal x plus 1, then we have our form that we need. H of x equals f of g of x, and we can use our formula h prime of x equals f prime of g of x times g prime of x. That gives us 3 times x plus 1 squared times 1, which is just 3x squared plus 6x plus 3, which is the same value we got before. So this is just another way to do it. With this particular example, it wasn't too hard to expand x plus 1 cubed, but it can get harder with more terms and more complicated terms. Alright, so in the multivariate case is very similar to a limit. We just hold all the other variables fixed and differentiate over the variable that we need. So consider the function f of xy is equal to x divided by y. What is the derivative of f with respect to y? So we don't write f prime of xy because of the ambiguity. Because are we taking the derivative of x with respect to x or y? It's not really clear. So instead, in this case, we have to use the other notation, which is df of xy divided by dx, or dy, sorry. So we're taking the derivative of f of xy with respect to y. And so if you use one of the handy-dandy rules on the slide, this slide, we can use the quotient rule. And using the quotient rule, we get 0 minus x divided by y squared, which is equal to negative x over y squared. All right, a continuation of the multivariate case. What if we wanted to differentiate with respect to x and y? So I mentioned earlier that these operators, dx and dy, they're actually, they can be treated like multiplicative factors. So what that means is that we could actually take the derivative of x first or the derivative of y first, because we can just switch the denominators. But since we already did the derivative of the inner with respect to y, we might as well use that in our computation. So we compute d dy and then d dx. So using the derivative of f with respect to y, we get d over dx times negative x over y squared. And we take the derivative of this with respect to x. Well, the negative 1 over y squared is just a constant with respect to x, so we get negative 1 over y squared. All right, so that is the bulk of the derivatives that you will need for this course. Again, I didn't actually use all of the tools in the example, but remember the chain rule. Remember the quotient rule. Remember the product rule. The common derivatives, I'm sure you don't really need to memorize that. You probably already know it. And the derivative of exponential function, that's important. And the derivative of a logarithmic function, that is also important. All right, so for an integral example, consider the probability density function for x, f of x equals 0.5 for x between 0.5 and 2.5. What is the probability x is between 2 and 2.5? All right, so let's consider the graph of f of x. These numbers might seem kind of small on your screen, but on the next slide it'll become more apparent. But this is just a graph that I made in Desmos. If you haven't gone on Desmos, it's like a website that you can graph any function. Super great tool for visualizing graphs. So yeah, feel free to check it out. I'm not sponsored by Desmos, but it's a good tool and it's free. All right, so here we have our function from 0.5 to 2.5. Hopefully that is easier to see, maybe like slightly. So we're considering what is the probability x is between 2 and 2.5, and we have our graph. So we're interested, this is 2 over here and this is 2.5. We're interested in the probability that x is between 2 and 2.5, and because this is a continuous random variable and we're given the probability density function, what does that mean? Well, hopefully you know that means we want the area under the curve between the value 2 and 2.5. And so because this is a continuous random variable, we actually don't really need to do anything fancy. We can just calculate the area manually because we know the height and we know the width. The height is 0.5 and the width is going to be from 2 to 2.5. That's just 0.5. And so we get the probability is 0.25. Therefore, the probability that x is between 2 and 2.5 is 0.25. And you might be thinking, okay, Stephen, we didn't use any integration. We solved this just fine. And that is true. And this is actually an example of a uniform distribution. With the uniform distribution, you can actually solve it without integration at all. But take a look at this. Take a look at this example. So if we move on to this example, we have how do we calculate the area if it's not a smooth function? So for example, consider the function f of x, which is equal to 0.5 times e to the negative 0.5x from 0 to 10. Well, if you're looking at 0 and, well, this is 0.2. Okay, it looks like I really zoomed in on this plot. But anyways, this is the shape of the curve, and it's going to be pretty hard to calculate the area of rectangles here because what is the height? We know the width, we can go from 0 to 0.2, but this height is constantly changing. So we can't actually use the technique that we used on the previous slide. Instead, we have to use integration. Alright, so I'm going to start with the definition of an indefinite integral. Again, knowing the definition isn't, it's actually, knowing the definition is important, but understanding the definition is more important. So, given a function f of x, an antiderivative of f of x is any function capital F of x such that f prime of x is equal to f of x. If capital F of x is any antiderivative of f of x, then the most general antiderivative of f of x is called an indefinite integral and denoted by this integration sign f of x dx equal to capital F of x plus c, where c is any constant. So we refer to f of x in this case as a function and capital F of x as the antiderivative of function f of x. So antiderivative. Okay, anti is not derivative. So in this case, we're actually performing the inverse operation. I don't know if that's the right term, but it's the reverse operation of derivative. So if we had a function that, a polynomial function that was x to the n, we are now, instead of taking the n down and putting n plus 1 or n minus 1 in the numerator, we're actually incrementing the numerator and then bringing it down, and so we get 1 over n plus 1. I'll show you some examples on I think the next few slides, but it's important to realize that relationship between the antiderivative and the derivative. So if we take the derivative of the antiderivative, capital F of x, we get the initial function. So this symbol right here is called the integral symbol, and f of x is called the integrand. X is called the integration variable, and c is called the constant of integration. Alright, so moving on to the definite integral. So again, this is a very technical definition, but it's important to understand what the definite integral represents. So given a function f of x that is continuous on the interval a, b, we divide the interval into n subintervals with equal width, delta x, and from each interval choose a point xi star, Then the definite integral of f of x from a to b is the integral from a to b of f of x dx, which is equal to the limit as n approaches infinity of the summation of I equals 1 to n of f of xi star times delta x. Okay, wow, this is quite a complex expression, but I'm going to break it down for you. So the left-hand side, well, this is like our indefinite integral form. But the only difference is we have a bound from a to b. So an indefinite integral does not specify the lower and upper bounds, and so we actually left them blank. But a definite integral specifies a lower and upper bound. And when we have a lower and upper bound, we can now represent this integral as what looks like a summation, right? And what are we summing here? We're summing this function value, which is like your y value, and we have a delta x. We have a change in x. So the x right here is actually, the delta x is actually referred to the width. So we have like a height times a width. Well, that's just the area of a rectangle. In fact, it's an area of the rectangle below the function in a way. It's an approximation because part of the height of this rectangle might go above the function. And that's why this itself is an approximation for the area under the curve. But when we consider widths or changes in x that are so small, and we consider in infinitely many sub-intervals, well then these widths just become points. And now when we're taking the area of a given like vertical point, basically a vertical line, we are now getting the exact area under the curve. And so that's what this is here. So this integral right here is the area under the curve f of x from a to b. So if capital F of x is the antiderivative of f of x, then we have that the integral from a to b of f of x dx is equal to capital F of b minus f of a. So this is our connection between the antiderivative or the indefinite integral and the definite integral. So we can use our indefinite integral and plug in the values a and b to figure out this definite integral value. This evaluates to a number since the constant of integration is both added and subtracted. So we didn't know what the constant of integration was because, let's go back here for a second. Oh, yeah, it's right here. Because when we were taking the derivative of f of x, there could have been a constant term that was not changing with respect to x that we got rid of. And that's why when we integrate, we have to bring it back. So that's this term right here. But because we have f of x or f of b minus f of a, the two constant terms actually cancel out. We get c minus c. And so we actually don't even need to include it when we're evaluating definite integrals. So in this course, we are most often concerned with definite integrals, which do not require the constant of integration. All right, so I've been emphasizing since the beginning of this review session that the interpretation of limits, derivatives, and integrals is very important. So in terms of integrals, integration is used to calculate the area between the curve or the function and the x-axis, or informally as area under the curve. That's usually how people refer to integrals. So for a probability density function, the area for a given x region is the probability of the variable being in that region. This is key, and this is why integration helps us compute these probability values. Integrals are also referred to as antiderivatives. This is because when you take the integral of a function, the result is like the reverse of a derivative, and that's where the name antiderivative comes from. If you're curious on more information, more formal information about an integral, please see this Wikipedia link right here. All right, so let's go on to, or let's look at example number 2 again, because now we understand what an integral is and how to use it to find the area under the curve. So we now want to find the area from x equals 0 to x equals 10. we are interested in the quantity f of 10 minus f of 0 because we're integrating this function f of x from 0 to 10. And we can use that by first solving for the antiderivative and then plugging in the values. So where f is the antiderivative of f. So capital F of x is equal to the integral of f of x dx, which is equal to the integral of 0.5 e to the negative 0.5x times dx, which is equal to negative e to the negative 0.5x plus c. This c is important for the antiderivative, but of course we know that we're going to be using the definite form of this, and so we could have just left out the c here, but I've left it in the slides just for completeness. So we have f of 10 minus f of 0. We plug in 10 in this first term, and then we plug in 0 in the second term, and we end up with 1 minus e to the negative 5. Alright, so here are some examples of integrals. I mentioned one earlier, but it might have been hard to visualize. I was talking about this integral right here. So the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, the constant of integration. Understanding all of these integrals is important for this course, and if you want to see more integrals, please see this source or this link. Alright, so one key part of integration is integration by parts, and I'm sure you guys have heard about this before. Maybe you still have nightmares about it from when you first learned it, but I'm going to cover it again because you will need to use this in this course, and honestly it's a great tool when you understand it because it makes questions a lot easier to solve. So consider the use of the multiplication rule of differentiation. So we have uv, we're going to take the derivative with respect to x, and this gives us the derivative of u with respect to x times v plus the derivative of v with respect to x times u, and that's just the multiplication rule in action. But now let's integrate both sides, all right, with respect to x. So if we integrate the left-hand side with respect to x, we're taking the derivative and then integrating, and because these are complementary operations, we're just left with our original uv. On the right-hand side, we have the integral of du dx times v dx. So we are initially taking the integral with respect to x, but we can actually treat these as multiplicative factors and cancel them out, and so we get the integral of v du. And then we have dv over dx times u dx, and we can cancel out these multiplicative factors. We can treat them as multiplicative factors, and we get the integral of u dv. So this is the end form that we have. And now what we want to do is, well, this form is not really useful as it is right now, but we can rearrange it to a form that actually does become useful. So if we rearrange this by moving this integral of u dv over to the other side, and you're moving the moving the integral of v du over to the other side, and then I just flip the equal sign. The rearrangement becomes the integral of u dv is equal to uv minus the integral of v du. Or in the definite case, the integral of u dv from a to b is equal to uv from b to a minus the integral of ab of v du. Alright, so now let's try to use this. Let's try to use this integration by parts to solve a question. So the question here is, let x be an exponential random variable with rate parameter 0.3. What is the expected value of x? So we want to solve the expected value of x is equal to the integral from 0 to infinity of x times f of x dx. So this formula right here, hopefully you have learned it, but if you haven't, this is a very important formula to know for solving, well, just for being able to answer probability questions in general. So we're looking at the integral from over all values of x, and then we take x multiplied by the probability of getting that x, or yeah, in I guess the simplified understanding is x times the probability of that x, but again, this is a probability density function, so it doesn't quite behave like the probability mass function, but we can interpret it like that for this case because we are summing over all values of x. And then we have dx. So we can substitute our probability density function in. And now before this would have been a little bit harder to solve. We'd probably need to do some sort of substitution. But we can actually solve this using integration by parts. And so this is our integration by parts formula. If you have not memorized the integration by parts formula or a variation, I know there's a lot of different ways to write out this formula. I highly recommend memorizing it because, well, you might have an open book test, but it might not be open book. So I recommend memorizing this formula. So the tricky part here is not memorizing the formula, unfortunately. It's knowing how to apply the formula to decide what is the u, what is the dv, right? So this is usually what we're given, and if we can change it into this form, it should simplify it. But it will only simplify it if we choose u and dv intelligently. So if we look at our function up here, we could assign u to be x, or we could assign u to be 0.3 e to the negative 0.3x. Well, what do we need to do with the u? We have u here, we have u here, and then we have du. So we need to take the derivative of u with respect to x. At some point, we're going to need to do that. All right, so if we consider these, well, which one of these is easier or is simplified when you take the derivative with respect to x? Well, this right here is simplified when you take the derivative with respect to x because this just becomes 1, right? Whereas this term right here, when you take this derivative, it will actually become more complex because when you take the derivative of an exponential function, you don't actually get rid of any of the x's. So we're going to assign u is equal to x and dv is equal to 0.3 e to the negative 0.3x dx. So this term right here does involve the partials right here, and we're going to use the partials for our integration. So we're going to integrate the left-hand side and the right-hand side. And if we integrate the left-hand side, we get v, because we're integrating with respect to v. And if we integrate the right-hand side, we get this term right here. And we're integrating the right-hand side, obviously, with respect to x. And then when we integrate u with respect to x, we get 1. And in fact, this du should be equal to dx, because the du over dx, when we move the dx to the other side, this should be du is equal to dx. All right, now we can plug these values in to our equation. So we have this to start, and now using our integration by parts rule, we get negative x times e to the negative 0.3x from 0 to infinity minus the integral from 0 to infinity negative 1 e to the negative 0.3x dx. So we can see here that the integration term that we have to do is a lot easier now because we only have 1x, right? So we did it right. If we ended up having a bunch of x's over here, or our term got more complicated, then we made a mistake, and that's when we need to reevaluate what we assigned to u and v, or u and dv. So because this is quite a large expression, I broke it up into a and b. So a is equal to negative x times e to the negative 0.3 x from 0 to infinity. And this is when we can use some of our limit knowledge that we reviewed earlier this session. So we're going to consider, instead of plugging in infinity in, because it's infinity, we're going to consider the limit. So the limit as x approaches infinity of negative x times e to the negative 0.3x. Well, this is going to be negative infinity, and this is going to be 0. So we have negative infinity, we have 0. So how can we kind of reason about this? Well, I believe you can use L'Hospital's rule, which is a way for solving undefined limits. Another way is to look at the functions themselves. And we can look at the rate. I mean, this is kind of using L'Hospital's rule, but the rate at which e to the negative 0.3x approaches 0 is a lot faster than negative x approaching negative infinity. And because it approaches 0 faster, that ultimately takes over and wins. And so this whole term becomes 0. Furthermore, if if this term became infinity, then it wouldn't be a probability. Like we cannot have I believe, yeah, for the exponential distribution, there's no way that it could have been infinity. So we would have made a mistake there, because we would have had negative infinity here and subtracting some number. So the first term is going to be 0, and then we're going to subtract another term, but when we plug in 0, that's just going to be 0, so we have 0 minus 0, which is 0, and so now we just need to solve for b. I'm going to take some water here. I'm talking a lot. Alright, so for b, we're interested in the integral from 0 to infinity of -1 times e to the negative 0.3x dx. We're going to continue that on this page. Okay, so when we integrate e to the negative 0.3x, we get 1 over negative 0.3. But in this case, we already have a -1 here, so they cancel out. And so we get 1 over 0.3 e to the negative 0.3x from 0 to infinity, which is equal to the limit as x approaches infinity of 1 over 0.3 times e to the negative 0.3x, excuse me, minus 1 over 0.3 times e to the negative 0.3 times 0. And we already kind of looked at a similar scenario. As x approaches infinity, this value approaches 0, so this whole term approaches 0. And we get anything to the power of 0 is just equal to 1, so we get -1 over 0.3. And so the expected value is a minus b, which is 0 minus -1 over 0.3, which is just 1 over 0.3. And if you memorize the expected value of a exponential distribution, which it could come in handy just to double check your answer, you will know that this is the correct answer, and this is actually how you get that expected value. It's 1, and in general, it's 1 over the rate parameter. Alright, so now we want to, just like derivatives and limits, let's consider the multivariate examples. So the multivariate examples we solve in the very similar manner. It's basically we just hold the other variables fixed, and we integrate with respect to whichever variable we're planning to integrate. So consider the integral of x, y with respect to integrating with respect to x. So because y is independent of x, we can actually move y outside of the integration. And so we're just integrating over x, which is just 1/2 x squared plus y, and then we need to add c. So I believe I may have made a mistake here. cy, there could be, is there a cy here? That's a good question. There could be a cy. Is it supposed to be c or cy? I'll leave it at c for now, because that's what I have in the slides. So similarly, if we want to integrate with respect to x and with respect to y, we can do this by integrating with respect to one of them first and then integrating with respect to the other variable. So in this case, if we integrate with respect to x first, we get the integral of 1/2 x squared y plus c, and then we're integrating this whole thing with respect to y. And that gives us 1 over 4 x squared y squared plus cy plus d, where c and d are constants. Of course, in general, the c and d aren't really going to matter because we're going to be doing definite integrals, and so the c and the d would cancel out. Alright, so that is all the material that I wanted to review. Now I'm just going to go over important takeaways from limits, derivatives, and integrals. So limits are useful when you're investigating a quantity of interest, when a quantity of interest goes to infinity. So when you want to see what happens to a function f when x goes to infinity, that's where limits come in. When the number of trials goes to infinity, such as an infinite geometric series, then limits will come in handy. And when upper or lower bounds goes to infinity, this allows us to verify valid distribution functions. When you think about limits, I want you to think as a variable, for example, x goes to a certain value or infinity, but isn't at infinity, what happens to our quantity of interest? If we're curious about this, that's when we use limits. All right, so for derivatives are useful when going from distribution function to probability density function, when you are considering a rate of change, and when you are trying to optimize a function. When you think derivative, I want you to think slope, or instantaneous rate of change, or tangent line. All right, now moving on to the summary for integrals. Integration is useful when going from probability density function to distribution function, when you are considering an area between the function and the x-axis. It really helps you, again, calculate probabilities. When you think integral, I want you to think, excuse me, antiderivative and area under the curve. Remember to include the constant of integration when needed. Again, I can't think of any questions where you need to have the constant integration, because most of the questions are definite integrals. But it's important to remember you want to use the antiderivative first and then plug in the values. All right, so there was a lot of information. I really wanted to try my best to review some of the distributions as well as cover limits, derivatives, and integrals. But as always, there's a chance that I left some information out, and some of the information might have spiked some curiosity or some more questions that you might have. So please feel free to post any questions you have on Piazza, or to come by my office hours on Wednesdays from 3 to 4 p.m. Or feel free to send me an email at steven.brock@mail.utoronto.ca. And as always, if you enjoyed this video, or if you think I could have made things a little bit better, more easier to understand, please let me know by sending me an email. But yeah, I really appreciate any feedback on the review session. Thank you very much, and best of luck with your studies.